Hi everybody. Today I'm going to tell you about Guardian Agent, a tool we've built for secure delegation for the SSH protocol. And towards the end of the talk, I'm also going to discuss how this tool we've built, as well as the principles behind it, allow us to address other authorization scenarios and not only SSH. But we're going to start with SSH, and we're going to see to see how delegation works today in SSH, let us consider the following scenario that many of you are probably going to be familiar with. So imagine a user connecting to some cloud machine of her choice, and that user wants to clone her private Git repository located on GitHub. And the repository being private, of course, cloning this repository requires the user to authenticate. But the private key of the user is located on her local machine, on her laptop, and obviously she would like to avoid just uploading and uploading her key to this cloud machine, which could be potentially untrusted. Well, this seems kind of like a kind of a basic scenario, and it also seems like the SSH protocol and the SSH tool chain are kind of thought of it, and we have a solution for that. So what can the user do? The user can run an SSH agent locally and add her key to that SSH agent. And to be extra secure, she's also going to add this -c flag that's going to ask, such that the agent is going to ask her every time her key is getting used. So she'll know exactly how the key is used. Then the user is going to SSH and enable agent forwarding when she connects to the cloud machine. And then when she runs that git clone command, the authentication request is going to get forwarded to the local agent, who's going to prompt the user to confirm the use of her key. And it looks like problem solved, so the user knows every time her key is used, she can confirm it, she can deny it, she has full control of her credentials. But if we look closely at this prompt that the user gets, you kind of see that it doesn't really provide us with the guarantee that we would want. So what does the user see on this prompt? Basically, she sees the path to her local key, not really the kind of information that you want to have once you're confirming the operation. And so when the user clicks OK, and she thinks she authorizes that cloud machine to clone her repository, if that cloud machine is compromised, or maybe the entire cloud provider is compromised, then, well, she thinks she's signing a challenge used for authentication to GitHub. That malicious cloud provider could actually use that signed authentication challenge in order to perform some different malicious operation on a completely different host to which the user has access. And what is kind of the root cause for this problem? Well, the root cause is that with the current way that this protocol is used and all the tools around it are built, that the user cannot really verify the identity of the delegate to whom she delegates her credentials. So when she sees this prompt, she doesn't really know, does the challenge originates from from GitHub, or does it originate from some different host? And also, the user cannot really verify the command that this authorization is going to be used for. And the identity of the server and the delegate both are kind of untied when she sees that authentication challenge. And it's important to stress that this is not merely a UI issue. So it's not just we could change that prompt and display some other, maybe more important information. In fact, this type of information isn't really available to the client. And of course, there are no any cryptographic guarantees that when you sign this challenge, what is this challenge going to be used for? So the picture today is that by approving this kind of prompts, we're essentially signing a blank check. So we put our signature there, and we don't really even specify the amount of money, what's the command that we're going to run. We don't specify the recipient, the identity of the server on which the command is going to run, and maybe even the identity of the bank. If I have multiple bank accounts, is also not set to relate to the previous talk. So what do we really want? So what we want is instead of having this kind of not very useful prompt that doesn't allow us to control the delegation, what we want to have is we want to have an authorization decision that has all the scope, all the necessary scope to make a meaningful decision. So at a minimum, we would like to know who are we delegating to, what can the delegate do with our identity, and to whom. So for example, what's the server to which the operation will be applied. And again, I want to stress out that it's not only a UI issue, but kind of a protocol there's a protocol issue here as well. And if you think that this is kind of an issue that's only present on SSH and other protocols get it right, well, similar scenarios, not exactly of this type, but similar scenarios involving unscoped delegation exist in other protocols as well. So for example, for TLS, we can consider the scenario in which some publisher wants to delegate the duty of serving its homepage to a cloud, to a content delivery network, a CDN. And of course, the publisher wants to still serve his homepage using HTTPS. So to do that, currently, what is required is that the publisher needs to give the certificate as well as the private key corresponding to this certificate to the CDN for the user to get an HTTPS connection. But once the publisher gives access to its private key to the content delivery network, if the content delivery network is compromised or is malicious, then it can use this credential to serve some other content. So in essence, the publisher delegates his identity without sufficient control. And there have been recent works, for example, the work by Cloudflare called Keyless TLS, which in essence is very similar to SSH agent and suffers from the similar problems. So with Keyless TLS, the solution works by the publisher keeping the private key. So in this picture, you can see that the private key is kept by the publisher. And then every time that the CDN wants to establish a secure HTTPS connection as the server, he's gonna talk to the publisher and send him a challenge and gonna get a signature or decryption depending on the encryption protocol used. So if you look at this solution, in essence, the reason that I said it's kind of similar to SSH agent is that the publisher really exposes a signing oracle here. So he tells the CDN, just send me those challenges and I'm going to sign them. Do I know how they're going to use? Not really. So if the CDN really wants to manipulate the content, he can do that. And for example, the identity of the client is also not verified in this case. So in our work, we started off by addressing the SSH issue, and we've built Guardian Agent. Guardian Agent is a tool that enables secure delegation for the SSH protocol. Our tool consists of an authentication agent running on the user's local machine, on her laptop. It consists of a custom SSH client that you can run on your cloud machines or any other partially trusted machine on which you want to run operations using SSH, but you don't want to put your key on. And the nice thing is that our protocol and our tools are backwards compatible with existing SSH servers, so you don't really need to modify the SSH server. So you don't really need to go and wait for GitHub to adopt our solution, and you can get practical security benefits today. So let me tell you about how does Guardian Agent work. So in the setting, we have the local machine that keeps the private key and running our agent. We have the delegate running the custom client, and we have GitHub as the server. So the first thing, when the delegate wants to run the command, instead of running the command directly on the server, he's going to talk to the local machine through the Guardian Agent protocol and request the agent to run the command and specify which server he wants to run the command on. Then the agent can prompt the user and make sure that the user actually approves the operation. And in this way, the Guardian Agent local machine gets the command, gets the identity of the server, and can also identify the delegate based on the incoming connection. Then, if the user approves the operation, the local machine starts a connection to the server, authenticates using the private key, and issues the command. So at least we can see that the local machine has control over all the parameters that we want to control, the identity of the server and the command and so forth. But this seems kind of naive in the sense that if we just do it this way, we're kind of losing all the benefits for which we wanted to delegate in the first place. So we really wanted to run the command on the delegate, and we don't want to run it on the local machine for whatever we wanted to do. And even tunneling the entire connection through the local machine isn't really practical, because imagine you're just riding on a train and you have a very bad connection. You don't really want to tunnel the entire Git repository you're cloning through your local connection. You just want to get it from the server to the delegate. So to do that, the final step of our protocol is basically handing off the SSH connection from the local machine to the delegate in a way that it's transparent to the server. This way, only the first part of establishing the connection, which is really minimal in terms of the required bandwidth, happens between the local machine and the server, and then the connection can be resumed directly between the delegate and the SSH server, so the entire contents of this, let's say Git repository in this case, will be transferred directly from the server to the delegate. How do we do this? How do we do this SSH handoff? And to kind of think of it abstractly, what we really want to do is we want to serialize the entire state of the SSH client, send it to the delegate, and then deserialize and resume the connection. But if we look at what does the SSH state consist of, it contains a lot of messy details. It contains of the session ID and the sequence number and all the details of the of what command I'm running, and most annoyingly, it has a lot of crypto details. So every time you establish an SSH connection, you need to negotiate an algorithm for key exchange and for macking, for encryption, and each such algorithm contains a lot of state that evolves as the connection continues. You have IVs, you have counters, and just serializing this in general would require either support from each individual cipher or having to fix the cipher mode, and we don't really want to do that. So to avoid doing this kind of messy serialization, what we do is we use a feature already provided to us by the SSH protocol, and this is that we can run a key re-exchange on an existing connection. And the nice thing about key re-exchange is, as you can see here, is that all the crypto state is actually refreshed when you do the key re-exchange, which is sort of what we need. So how do we use this key re-exchange? So we start by having two separate SSH connections, one between the delegate and the local machine, and a second one between the local machine and the server. And initially, those two connections are independent. Then, after the local machine has sent the command on its connection with the server, and a key re-exchange is triggered on both connections. But this time, the parties in the key re-exchange are the delegate and the server, and the local machine only acts as a relay that passes around the key exchange messages. And kind of as a basic property of key re-exchange, what you end up having is a shared key between the two endpoints, namely the delegate and the server. So once we're done with the key re-exchange, we essentially have an SSH connection now between the delegate and the server. And there are a couple of the messy details that you still need to take care of, but they're very minimal and don't depend, for example, on the crypto being used. And one last thing that needs to be taken care of is that we want to avoid the delegate being able to issue additional commands after the handoff. So to do that, before we initiate the handoff, we use an already existing extension to the SSH protocol available in OpenSSH called No More Sessions, which allows the local machine to request from the server not to honor any additional commands that's going to be issued after that. This essentially locks down the session to the particular command. And maybe something that jumped to your mind while I was describing this, where we also have a couple of constraints on the transport layer that we need to take care of. For example, the agent might not even have direct connectivity with the server, because maybe you're connecting to the delegate and it needs to connect to some server which is not accessible from your local machine. And second, as I've told you, we want this to be fully compatible with existing servers. So the entire connection, this entire handoff needs to be transparent from the server's point of view. So to address both of these concerns, what we do is that the delegate acts as a relay on the transport layer between the local machine and the server. And then after the handoff, he can reuse the same TCP connection to talk to the server directly. So this achieves both benefits. So this relay allows the local machine to have connectivity with the server, and also from the server's point of view, throughout the entire connection, he talks over the same connection, and it looks transparent to it. So Guardian Agent, we implemented Guardian Agent. It is available and already used by people online. So I invite you to go on GitHub and use it. And kind of in the remaining part of the talk, I want to kind of discuss about how Guardian Agent, both as a tool and those fine-grained fine-grained delegation principles can actually be extended to additional settings. And specifically, I'm going to talk about privilege elevation. So what's privilege elevation? So I think most of you are, again, familiar with the need to run the sudo command, for example, to install some program. And the reason that you need to do it is, well, you usually run using some unprivileged account, and you have some operation that you want to do, which requires more privileges. And so, again, sudo is kind of ubiquitous. You run it, and then it asks you for your password. And once you confirm your password, the entire process runs as root. So what's the problem with this? So there are kind of two issues with it. The first issue is that if you hope that sudo would allow you to have some security separation between your unprivileged account and your privileged account, then it doesn't really do that. And specifically, it doesn't really withstand an attacker that manages to compromise the unprivileged account. Such an attacker can, for example, wait for you to run sudo for some legitimate cause, and then try and fish your password, modify the command, and this can be done using like very basic modifications even to your shell scripts. So sudo is still good for preventing yourself from making mistake, but it's not. I kind of claim that it's not really suitable to give this extra security guarantees between your unprivileged account and the root account. And second, if you look at the way that this mechanism works, is that after you approve the privilege elevation, and even if the program to which you gave these elevated privileges is a legitimate program, it is in fact the one that you want to run, you still kind of give it full root privileges that are unrestricted in scope, and so you're allowing it to do anything that root can do rather than perhaps a single operation that you wanted to give it these extra privileges for. And this is dangerous, both because programs can be exploited either due to memory bugs or some logical security bugs. And whenever this privilege, you basically increase your attack surface, because whenever this privilege process gets compromised, you lose full control of your machine. So our idea is kind of to use the same principles behind guardian agent to solve this problem, or maybe not to solve, but kind of improve the state of the world when it comes to privilege elevation. So how are we solving this? So again, consider the scenario where we have a local machine, and the one that has your credentials, the one that you use locally, and now consider a case when you want to run sudo on some remote machine. And I want to know that the same kind of principles can be applied to running sudo even on your local machine, but then you need to take care of trusted path issues, such as you still need to have somewhere when you can enter your password or interact with the machine in a secure way. But for simplicity, let's just look at the remote scenario. So with our solution, instead of running the apt-get a binary using sudo and elevating the entire process, the process is going to run using the normal user privileges. So this obviously won't work. So what we do is that we run a separate privilege daemon that will take care of elevating privileges in a much more fine-grained way. And we also have a small library running within the unprivileged process. So everything on the left here, the apt-get process and the library is unprivileged, and we have one privileged daemon. So when the apt-get process is going to do some operation which requires those extra privileges, the one that we actually originally needed sudo for, then obviously this operation is going to fail. So for example, in this case, it's going to try and open some protected file which you cannot write as an unprivileged user, and the operating system is going to tell the process, well, you can't do that. Access is denied. In this point, our library is going to intercept that system call just before it returns to the program, and request the authentication agent running on your machine to approve this operation, which was originally denied. Again, same as before, now the user can be prompted. He can make sure that he's approving whatever he wants to be performed on that remote machine. And once the operation is approved, a signed approval using the user's private key is sent from the local machine to this library running in the unprivileged process. Now, this unprivileged process can present the signed approval to the privileged daemon and request for this operation to be performed on its behalf. The privilege daemon verifies the signature, verifies the parameters of the operation, and then goes ahead and performs this operation from the privilege context. In this case, for example, it opens the file, gets the file descriptor, and passes the file descriptor back to the unprivileged daemon. So as you can see here, as a result, we've managed to perform a privileged operation from an unprivileged process without, first of all, by allowing the user to control this specific operation, and without increasing the attack surface and running the entire process as root. So this is kind of what we're working on now, and it turns out that kind of this personal authentication agent that we're building opens also new opportunities for other things to be done. So once we have this one focal point for all authorization decisions for the user, this allows us to look for other new possibilities. For example, running a personal authorization log that will have a log of all operations that were performed using the user's identity, and allow the user to ask questions such as, how was my identity used, what privilege operations did I prove, and make sure that his identity wasn't misused. And second, once all operations on behalf of the user kind of are strongly tied to the user's cryptographic identity, to his private keys located in one place, we can then go and maybe think about other scenarios, such as splitting the key between the user's hardware token and some trusted server in a way to enable things such as two-factor authorization and so on. So kind of to conclude, I think that the main point that you should take away from this talk is that we want to give users the power to really control the way that their identity is used, not only to control every operation individually with a much finer scope. And Guardian Agent is a step towards this. We provide secure delegation for SSH and also secure privilege elevation. Thank you.
OAuth 2 is becoming quite popular, and it's an authorization framework rather than an authentication one. How would that affect the kind of thing you're doing?
So I think for OAuth 2, it doesn't really use cryptography to assert every authorization operation that you do. So you kind of need to again trust some third party to store your tokens and so on.
How do you handle, so for privilege escalation, you have to deal with state on the server. So for example, if you have a symbolic link and the user approves access to the symbolic link, but then the link changes, how do you handle things like that?
So actually, symbolic links is really a source of kind of trouble. But what we do is we try to dereference all, as much as the state as possible from the unprivileged context. So for example, all symbolic links or relative paths are evaluated in the unprivileged process, and then when the user approves a path, he gets an absolute path that he can assign some trust to.
Cool. Yeah.
Isn't there kind of an inherently a time to check, time to use problem there, even with dereferencing all the symbolic links?
Yeah, so I think one idea that we have to address these kind of issues is, for example, maybe not blocking, but alerting the user if any component of the path, let's say for file operation, is writable by the unprivileged account. And you can kind of think of an invariant, if all the components of the path are not writable by the user, then it's not really, it shouldn't be susceptible to this kind of attack, at least from, there's still global state whenever you do, which can be modified concurrently. But I think it can minimize the risk of that.
How the user is allowed to perform actions on machine A, not on machine B?
So
if user is allowed to say run apt-get on machine 1 where she's on it, but then she is not allowed to run on machine B because it's only command.
So from each machine keeps a set of public keys that corresponds to the users that are allowed to do this operation. This is from the server's point of view. And from the agent's point of view, when the user authorizes something, it's actually presented also with the identity of the. So in the example that I gave, you will not only see that you are approving apt-get, but you also see the identity of the machine. And this identity is going to be inside that blob of data that you're going to sign. And then each machine can verify that its own identity was signed by the user.
How does the mechanism seems a lot like what Windows does. How does the user actually know the answer to the question that the user is being asked?
So I think you're bringing up two important issues. First of all, I think if you compare it to, let's say, the UAC mechanism in Windows, so although you are given some prompt, it still suffers from the problem that the entire process gets elevated after you approve this thing. So you still suffer from increasing the attack surface. About the point that the user needs to make a decision, then kind of our hope is that on the agent side, using the policy, we can kind of present the question in a meaningful way. For example, not only show the full path, but give some meta information about it.
I guess the answer that I sort of saw to my question was actually the authorization log, that you could at least forensically go back and say, although you didn't understand that you were authorizing this, you did actually authorize this, and this was the thing that caused you to be broken later. Would be improved.
Yeah, good point.
Yeah. Great, thanks, Dima.